Hello everyone, welcome to Chapter 18, Lecture 2 video. In this video I'll be discussing the substitution reactions of carbonyl derivatives under various conditions. So by the end of this video you should be able to draw mechanisms for acid-catalyzed acyl substitution reactions. If this sounds like something you might already know, it's because we have indeed covered this a little bit in class. We've been going over these things and interleaving these concepts throughout the class, so some of this will be review. We're going to cover it in a little bit more focused detail, paying a little bit more attention to the nature of the electrophile and the nature of the nucleophile and how that affects reactivity. Along those lines, by the end of this video, you should be able to draw mechanisms for base catalyzed acyl substitution reactions. We focused on more neutral and acidic substitution reactions until now. We can do substitutions under highly basic conditions with really strong nucleophiles. These occur in the absence of acid, i.e. basic conditions. And we'll be talking about what leads to that. And finally, you should be able to explain and predict trends in reaction mechanism among a set of nucleophiles by applying knowledge of relative nucleophilicity and basicity. What does this even mean? Well, these substitution reactions overall are an interplay between nucleophile strength and electrophilicity of the carbonyl derivative. That is to say that when we're considering all of these examples, we want to consider both how strong of a nucleophile the substituting group is and how strong of an electrophile the carbonyl derivative is. And so not all the same rules apply for the same exact substitutions. It's a two-component problem, and we'll talk about various instances of that. So with our first example, we're going to talk about acid chlorides. Acid halides in general are extremely reactive. If you open them up in lab, you sometimes see a little bit of hydrochloric acid fuming out of the top of the container. That's because they react with water, which is a weak nucleophile, to generate carboxylic acids. Here we have a mild base catalyzed or mediated substitution. In this case, we're going to use our H-nuc is going to be HNR2. Okay. And HNR2 is able to add in without any help to an acid chloride. This is because secondary amines, which is what's represented here, secondary amines are decently nucleophilic. We do not need to use an acid to catalyze this addition. Our carbonyl is already electrophilic enough. This chloride here is electron withdrawing and helps increase the electrophilicity of the carbonyl. As I said on the previous slide, these substitution reactions are a two-component problem. How strong is our nucleophile and how electrophilic is our carbonyl derivative? Here we have a highly electrophilic carbonyl derivative and we have a decently nucleophilic amine. So what that gets us to is the key tetrahedral intermediate and our Zwitter ion. I'll draw in both the R groups this time. Nothing has changed in our amine. I'm just drawing them out this time. And it is an ammonium. We haven't lost that proton next door yet. The plus charge is best drawn on nitrogen. And our chlorine is still attached. This is our key tetrahedral intermediate. This is the attack phase of the mechanism. Okay. And the next step of the reaction, we have our mild base come along and deprotonate the amine. Now in this case, that mild base is pyridine. The conjugate acid of pyridine has a pKa of about 5. This means it's a mild base, not too strong, not too weak. And this leads to the anionic tetrahedral intermediate. And this collapses to afford the substituted product. In this case, nucleophile equals NR2. This is a relatively straightforward mechanism. But what do we mean by this or two equivalence of HNR2? Well, sometimes chemists are lazy and they don't want to weigh out pyridine and their amine base. So they just add more amine. And in this or two equivalents of HNR2 scenario, we just have a second equivalent of amine come along and act as a base. Remember, our nucleophile can also sometimes act as a base. And that's all that's occurring here. If pyridine can do it, then a secondary amine can also affect the transformation. And that's really all we're saying is here there's one equivalent that comes in, and the second equivalent acts as a base. That's all that statement means. All right, moving on to the next example. In this case, we have another reaction of an acid halide, specifically propionyl chloride. And we're substituting using a sodium carboxylate, this compound over the arrow. Now, if we think about the sodium carboxylate's conjugate acid, something of this form over here, the pKa of the conjugate acid is actually decently low. 4.5 is what's considered a modest acid. It's not strong, but it's certainly a reasonable acid. It'll protonate various things. Notable example of this is acetic acid in vinegar. It has that characteristic vinegar smell, and it has a pKa of 4.5. If you have highly concentrated vinegar and you sniff it, it'll kind of burn your nose. And that's because it's a modest acid. So the reason I'm telling you the pKa of the conjugate acid is that oftentimes acidity is inversely correlated to nucleophilicity. So what I'm trying to say here is that carboxylates are not strong nucleophiles. They're not extremely weak nucleophiles like chloride is, but at the same time, they are not strong nucleophiles. And this speaks to the overall electrophilicity of our acid halide. Our acid halide still reacts with weak nucleophiles like carboxylates to afford the anhydride product. And so this is the reason this reaction proceeds is because our acid halide is so strong. If this were an ester, we would not expect a substitution reaction because esters are not nearly as electrophilic as acid halides. So how does this reaction work? Well, this reaction works very similar, in fact, even easier than the previous example. I'll draw out the lone pairs to emphasize that it is an anion. Again, it's not a strong anion, but it is an anion nonetheless. It's a modest nucleophile. You'll note this is quite similar to our last mechanism where we end up with a tetrahedral intermediate. Or chloride attached. And since chloride is an excellent leaving group, just like the time before, what we do is we go to product. Okay, so this is a relatively simple two-step mechanism. We have the attack phase, and we have the, what I'll call collapse phase, where our tetrahedral intermediate collapses to re-afford a carbonyl compound. And what we end up with here is plus Cl minus plus Na. Those are our two salts. Now, one thing we don't want to see, and you may start to get really comfortable with these mechanisms and start to think about going through some shorthand. What we don't want to see is something like this. I'm going to give it a big no. We don't want to draw all of our steps in at once. If you've been doing the homework and you get really comfortable with this and you say, why do I have to draw all these intermediates? You might see something like this, and that's a no. We do not want to do that, okay? So we have to show the key tetrahedral intermediate, okay? You cannot do this all at once. It is not correct and you'll be marked down. Even if you know exactly how the electrons are flowing, you need to show these intermediates, the attack and collapse for the simple two-stepper. All right, so we just showed an example of a modest to weak nucleophile, acetates, attacking a highly electrophilic acid chloride. And the reason this reaction proceeds, again, is because acid chlorides are just that electrophilic, that even modest nucleophiles will react with them. Of course, strong nucleophiles will also react with acid chlorides. But there are other examples here too, where we have even weaker and weaker nucleophiles. So we'll show this again. In this case, we'll use a molecule called acetic anhydride. Acetic anhydride looks something like this. Not something like this, it is exactly this. And it's not quite as electrophilic as an acid chloride, but it is still highly electrophilic. And that's because the group off of our carbonyl, the acetate, is a good leaving group. Its conjugate acid has a pK of about 4.5. And our nucleophile in this case, highlighting all the important parts, this is our nucleophile, put it in parentheses. Our nucleophile is a weak nucleophile. Alcohols are not strong nucleophiles. However, again, we have a strong electrophile, acetic anhydride. And so the way this reaction works is our lone pair reaches out and attacks the carbonyl of the acetic anhydride. This should look pretty familiar at this point. We get to a tetrahedral intermediate. Remember, we haven't lost the proton off of our alcohol yet. It's a weak nucleophile. We haven't done anything to get rid of it. Now in comes the other component of this, the pyridine. Py means pyridine. I'll draw out the structure of pyridine here. It smells horrendous. It's a terrible chemical to have to use. But it's quite useful because it's a relatively modest base. Its salts can be washed out of solution. Organic chemists have to think about how they're going to remove reagents and purify the compound that they're interested in. And so they're usually pretty excited when they can wash something out with water because organic molecules typically are insoluble in water. So we get to our key anionic intermediate. This looks quite similar to our amine nucleophile example that we did on slide 2, wherein our nucleophile attacks, we deprotonate, and then we have our collapse phase that kicks out our leaving group. And in this case, this leads to benzyl acetate is the name of this product. It also leads to acetate leaving group and pyridinium, the conjugate acid of pyridine. And so one thing we might want to ask ourselves when going through this mechanism is why didn't we give ourselves a good nucleophile to start? That is to say, why didn't we have our pyridine attack our benzyl alcohol? Benzyl alcohol in this case is our nucleophile. Draw it out again here. Why didn't we have our deprotonate and go to pyridinium and the corresponding benzyl alkoxide, which is this molecule here? Well, the pKa of this molecule up here, the benzyl alcohol, is about 17. And the pKa of our pyridinium is about 5. Now, does that satisfy our within our pKa gap that we've been using of sometimes 8 or 9 units? No, it doesn't. So the pKa's of the two acids that we're comparing, the conjugate acid of our base and the acid of our nucleophile, the benzyl alcohol, they're not within the required number of units. So it's too much. Pyridine is too weak a base to deprotonate it. And so that's why we draw the alcohol attacking before it's deprotonated. This compound down here, this tetrahedral intermediate, this will have a pKa of about -1, -2, -3. It doesn't really matter. It's a much stronger acid when it has this extra oxygen-carbon bond. All right, this brings us to our next example where we are using the amine analog of the previous example on slide 4 to react with acetic anhydride. Again, a great electrophile. So what does this look like? Well, one thing I want to note right off the bat is there's no added base. And the reason for that, and we'll see in a second, is that when we have these strong electrophiles, we have to be really careful that our base won't react with our electrophile. So let's say, for example, over in the bottom corner, we used our acetic anhydride. And we said, hey, we're going to use sodium methoxide as a base for our amine coupling. And what we would actually get is our alkoxide is a very strong base, but it's also a decent nucleophile. And what could happen is that could attack faster, and what we would get to is something like this. Instead of the desired product, which is the amine substitution. So we have to make sure when we're considering all this that our base is not so strong that it will react with our electrophile. One of the easiest ways to do this is just to throw in two equivalents of the nucleophile that can also act as a base. There's no chance for anything else to react because there's only one molecule. Our nucleophile is also our base. What does that look like here? Well, we talked a little bit about this on slide 2, but our nucleophile can add into our acetic anhydride. We've seen this before. Again, pH just means phenyl. Phenyl is a 6-membered carbo cycle up here. There's a lot going on there, but this is our Zwitter ionic tetrahedral intermediate. And then here, what we can do is we can use more benzylamine as our base. And this avoids the cross-reactivity potential of our base inadvertently reacting with our strong electrophile. And the lone pairs on our alkoxide intermediate will come down and kick out our acetate leaving group. All right, and one thing I didn't draw over here was the conjugate acid of our amine base. That balances the charge. And our counterion to that compound is the acetate that leaves. So it'd be this ion pair. And now the pKa of this compound here is about 9. It's not resonance, just an arrow. And these could be in equilibrium because their units, pKa units, are so close together. You may have a little bit of acetic acid mixed with this. However, because the pKa of this is about 5, our equilibrium is going to favor where the stronger base is protonated. Or it's going to favor the weaker acid is another way of saying it. Let's correct that. It looked like it said -9. The pKa is about 9. So again, we want to protonate keep the weaker acid protonated. And so equilibrium favors the top, but these are close enough in pKa, 4 units, that they will interact and be in equilibrium. Right, so in our next example, we're going to talk about the addition of weak oxygen nucleophiles, that is things like water, alcohols, to esters. And because we have a weak electrophile, esters are much more stable than acid halides or anhydrides that we just talked about. And we have a weak nucleophile. We need to activate our carbonyl. This reaction is called a transesterification in both these instances. We're going from an ethyl ester to a methyl ester. And this mechanism occurs through essentially the same mechanism as the Fischer esterification. However, we're starting with an ester. So that's why we call it a transesterification. And this combo you see here, this acetyl chloride, we can essentially make this into HCl. So the acetyl chloride reacts with the methanol to generate HCl and methyl acetate. And this HCl can then go on to activate the carbonyl of interest. And so this is just a convenient way of making anhydrous hydrochloric acid. Normally when you buy hydrochloric acid, it comes along with some water, and the water reduces the reactivity of the HCl. So this proton will generate an activated carbonyl. And again, we have to activate it because esters are quite stable. The electrophilicity of the carbonyl carbon is reduced by the resonance contribution of the oxygen onto the carbonyl carbon. So just to reemphasize it for the final time, these substitution reactions are an interplay between the electrophilicity of our electrophile and the nucleophilicity of the nucleophile. If we have a weak electrophile, we need a strong nucleophile. Or we need to do something to increase the electrophilicity of our carbonyl. Here we're increasing the electrophilicity through the activation step. We're activating it with the acid. This makes it a strong electrophile so that our weak nucleophile can actually attack. Now, as I work through this example here, again, we're doing this proton shuffle that we're so used to doing. And we're trying to improve the leaving group ability of what needs to leave. So this leads to our protonated methanol, which was just acting as the conjugate base. This is approximately the same acidity as protonating this group here. So we're just doing this proton shuffle we've done so many times before. And that is to activate our leaving group of the ethyl group. And that makes it a good leaving group and leads to our protonated ester. Which, when deprotonated, leads to product. Now you may have noted I started over here with this HCl example, and I ended up over on this example of tosylic acid methanol. In this case, these reaction mechanisms are identical. We have just changed the acid. So again, this acetyl chloride methanol combination that generates a more anhydrous hydrochloric acid, and that's necessary to help improve the protonation of our carbonyl to activate it. We could also use Tossic acid for this as well. And so these mechanisms are the exact same. The only difference is what acid do we use. And Tossic acid is a very strong acid, so it fulfills the exact same role of methanol. Now on your own, and this is something we've gone over in class, think about the hydrolysis of an ester using sulfuric acid. All right, so in our final example, we're going to do the base-mediated hydrolysis of an ester. In this case, we have lithium hydroxide instead of the weak nucleophile of water earlier, or methanol. So this is an anion. We think about it as this lithium plus and this OH minus. And this really amps up its reactivity such that now we don't have to activate our carbonyl. We can just go straight into it. And again, this is that interplay. Now that we have a strong nucleophile, a highly basic nucleophile, we can go straight into it. We don't need to activate our electrophile to make it more electrophilic because our nucleophile is good enough to get the job done. This is another simple mechanism wherein we kick out our ethoxide to finish this out. Now, one thing to note, lithium ethoxide, molecule drawn here, is a strong base. Carboxylic acids are modest to strong acids. So what really happens here is our real product, until we acidify, it's going to be the lithium carboxylate and ethanol. And again, if this is unclear to you why this would be the case, analyze the pKa's and make sure you're comfortable with why ethoxide would quantitatively deprotonate this propionic acid, the product. And now on your own, you can think about how this would work for a transesterification mechanism. Again, transesterification is where we go from one ester to another. And this mechanism is indeed quite similar. So take a moment to do that and convince yourself of why you need to do each step.